All right, so now we're ready to start looking at how to calculate some various macroscopic properties using our statistical mechanics equations. So now that we have our canonical probability, we can determine our average macroscopic properties. For example, let's calculate our average energy. We know that if we take our microstate energies and multiply them by their occupations, add those all up, we will get our overall ensemble constant energy. If we were now going a different way, if we were to multiply the average energy, okay, by the number of occupations, we would also get our ensemble average energy. In this case, this is like saying we know that we have an average energy for each of our microstates. Some may be higher, some may be lower. If we take the average for all of them, and then we multiply them by the number, okay, the total number of the occupations, we should recover our overall energy as well. All right, so using those two equations, we can figure out that the average energy is therefore going to be the sum of the A sub j's times our E sub j's divided by our overall occupations. All right, now I'm going to move that A inside of my sum, and then I have A sub j divided by my big A. Well, A sub j divided by big A is our probability of the jth state, and so therefore if I sum up the probability times that particular energy, that will give me my average energy. All right, the next thing that we can talk about is our Boltzmann distribution, okay, and that's going to allow us to get relative populations as well as different populations within our states. So we know that our probability function is equal to the n sub j divided by the sum of all my n sub j's. Again, this is the number of particles in a particular state. And then I can do that by taking my n sub j divided by my total n. Also, from StatMech, we know that the probability of the jth state is equal to the exponential of the negative beta E sub j divided by our canonical partition function. Now, from the partition function, it can be shown that beta is equal to 1 over kbt. I usually leave that as a homework problem. Now, in this case, kb is equal to our Boltzmann constant, which is 1.381 times 10 to the negative 23rd joules per Kelvin. Now, by combining this information with our probability functions above, we can get our relative population states. So, for example, let's say that we have two conformations and of a particular molecule, and they have a difference in energy of 8.3 times 10 to the negative 21 joules per molecule at 20 degrees C. Then we know that we can figure out our overall occupations, or overall, not our overall occupations, our overall number of particles. Okay? Now, n in this case is going to be equal to the sum of the exponential of negative beta E sub I, which, since I have two states, is equal to the exponential of negative beta E1 plus the exponential of negative beta E2. Now, we also know that E1 can be set to 0 because I can arbitrarily set my energy to a particular value for my lowest energy. I'm just shifting all of my energies up or down, okay? So I'm going to pick my lower energy to be 0, and therefore, because I know that E2 is this much higher, then I will end up with E2 being equal to the 8.3 times 10 to the negative 21 joules per molecule. That means that my n value is going to be 1.12. Now, if we want to know the probability of molecules in state 2 out of the total, then the probability of molecules in state 2 is equal to the number of particles in state 2 divided by my total number of particles. So this is going to be the exponential of negative 8.3 times 10 to the negative 21st joules per molecule, and then I am dividing that by, because it's my energy, I'm dividing that by my kb times my t. All right? Now, I then will divide that by my 1.12, which was my total occupations, and then that would give me a probability of that state of 0.11. So that means about 10%, 11% of my molecules are going to be in that second energy level. All right? Now, in general, we can also use this to any two arbitrary states where we have the relative populations of Ni, state I, is equal to, or relative of I relative to J is equal to the exponential of negative beta EI over the exponential of negative beta E J.